So then, welcome to the workshop Control Your Effects by Michael Sperber. And before we begin, I want to mention that there's a YouTube live stream. If you're watching from the live stream, please note that there's also a Zoom meeting and a Slack channel. You can ask questions in both of these, and you can find the link to those in the video description. Please note that there's the YouTube live stream, so if you ask a question and you have your camera on, then you will be seen on the YouTube live stream and afterwards in the recording. So Mike Sperber is a researcher of functional programming. He's been a practitioner and he's been an educator. He's been working on functional applications for a long time, and he shares his experience in various publications, both academic and industry publications, and he gives a lot of talks on conferences. And I'm happy that he's doing so today at MuniHac, and his topic is effect systems. So you may know that there's been increasing attention on effect systems in Haskell. And today, Mike is going to shed some light on what they are, how they can help you structure your applications, and whether you should use them. So, Mike, please.
Yeah, many thanks for the kind introduction. I guess I need to remember that we're also streaming on YouTube. So I think I'm going to start by saying that there is a GitHub repository if you want to follow along on your own machine. I think this is it. I've already posted the URL for this in the Slack channel, but if you're watching from YouTube, it's in Mike Sperber Haskell effects tutorial, and there's a bunch of code there. So you don't need to check it out in order to follow along with the tutorial, but just if you want to try out the code yourself or play with it, then yeah, go check it out. And there's also some instructions here in the README to get it set up. One thing that already came up in the discussion beforehand is that I think the latest GHC 8.10 is probably not going to work yet because, as we'll find out, a lot of the libraries that do effect systems really use quite recent features in GHC, and they tend to break when those features change in GHC. And I think polysemi, one of the effect libraries that we're going to look at, only works with GHC 8.8. So having said that, so in general, so the thing is, Zoom always plays hide and seek on my screen, so it just switched to a different screen. So it's all usually going to take me like a little moment to switch from here to the slides that you can hopefully see now. So one thing, I mean, you're always welcome to contribute to the discussion via the Slack channel, but I think this tutorial format works best when you ask questions right there smack in the middle, and hopefully we can generally just have a discussion on these things. So feel free if you have any question or any comment also. As you'll see, I'm not a super expert on all of the matters that I'll talk about. Please just jump in, unmute your microphone, and say something. I can see that there's 12, 13 people in the room right now, and I've taught a couple of tutorials with this format already, and that should work quite well with a number of people. So don't be afraid that there's just too many people wanting to jump in or whatever. I think things are going to work out just fine. Okay, and as to the general format, I think this is supposed to be a 3-hour tutorial, so it runs until I think 6 o'clock in Central European time, and we should probably take a break somewhere in there. My guess is that it should be about at the halfway mark, so at 4:30. Any questions so far? Already, okay. Okay, so you should see my slides. Tim was already kind enough to do most of the introductions. So I'm CEO of a company called Active Group. We do, what's maybe relevant is that we do software development in many functional languages, not just in Haskell. And so in particular, I'm only an occasional Haskell user. And that's going to be relevant for this tutorial. And so feel free, if I'm not using the right Haskell idioms, then please come in and fix it. And so one thing that's maybe also relevant for this tutorial is that we do a fair amount of training and coaching in functional programming. Specifically, we offer actually a certified training, if that means anything to you, on functional software architecture. And one of the pillars of sort of functional architecture is that you control your effects, which is the title of this tutorial. And we'll see how that all ties together. We also run a German blog on functional programming, if you're interested, and which has things on Haskell, but also on other functional languages. More importantly, we also run a developer conference, usually in the winter, called Bob, which also often has lots of Haskell stuff and lots of stuff related to functional programming, but it's not restricted to either of those. So we have all kinds of stuff. So Bob is always about the best in software development. I should probably add a note there that, well, usually we have it in Berlin. I'm still sort of hoping that we might do it on site, but of course, we can't be sure. So either it'll be on site or online, but we already know it will be on February 26th. If you look at the website, it's not even there yet. And the keynote will be done by Jeremy Gibbons. And I'm sure Jeremy will say something Haskell related in some sense. So, so with this tutorial, I'm going to go through a particular example that has to do with effects in Haskell, and that is discrete event simulation. And let me provide a bit of context. A couple of years ago, I was cooperating with actually the Bundeswehr Universität, the University of the Armed Forces in Munich, on a project that had to do with production automation. And they were doing a lot of simulation. And they said, well, the simulation that we do is we use something called discrete event simulation. And this discrete, and we always program it, in Java. It works just fine. And in particular, when they listened to me talk about functional programming, they were saying, yeah, all this is fine with the pure functions and so on, but discrete event simulation is really about simulating things in the real world, and they have state. So how do you deal with that in functional programming? I said, no big deal. Please, why don't you give me like a minimal discrete event simulator written in Java, and I will then show you how to do this in a functional setting. Shouldn't be a big deal, right? And so they did, to my surprise. They actually, a couple of months later, they sent me a minimal discrete event simulator in Java. And I thought, okay, well, let's show how we do this in Haskell. And then I discovered it's not as easy as I thought, right? And so I think everything in this tutorial, I mean, there's two things that are relevant. First of all, does it do what it should do? Does it work as it should? Are the abstractions right, and so on? But also, I think it's important. I think often in the Haskell community, we lose sight of sort of the didactic effects, right? We fall in love with all these fancy abstractions and with the 17 compiler extensions that we can turn on that allow us to express something intricate in a very neat fashion, but that require lots and lots and lots and lots of introductions and background explanations in order to show how they work. And so I've been trying to I've been struggling with this aspect of programming in Haskell, not just how the programming works and if I can get it done, but whether I can teach it to others. And that's proved to be unexpectedly difficult. In fact, very much more difficult than I thought. And so those are kind of the two aspects that are going to be crucial for this tutorial. So, and as I said, it'll mostly consist of us going through this example and look at it from various different angles, and then show sort of how the available solutions to that actually have evolved. So as Tim pointed out, there's been a lot of recent research in effect systems, and when I did this a couple of years ago, a lot of that was not available yet. Despite the fact that Haskell's been around since the late 1980s. I was quite surprised that there weren't sort of more convenient solutions to the problem. Okay, so that's the setting for the tutorial. Any questions or remarks or things that are important to you that we should cover? as I said, when you have anything, any comment, feel free to either post in the Slack channel or just unmute yourself and jump right in. So as you can see on this slide, that's a general picture. So what they did is, I actually didn't know anything about discrete event simulation, and they just sent me the code, but just to sort of illustrate what goes on is that, so discrete event simulation, sort of in the middle here, you have what's called a model. And the model is just essentially a big piece of state that describes what's going on in whatever it is that you're simulating. Typically, a model is just going to be a collection of sort of key value. It's essentially a key value store, as we will see. So and what happens is, well, it's discrete event simulation. So there's something called an event. And an event sort of has two aspects to it, as you can see. So an event contains, so when an event happens, it's something that happens. And when it happens, it causes a change in the model state. So there's a state change associated with the event. And also the event kind of spawns off other events by way of transitions. So we'll see all that in the code in a minute. So an event contains both a bunch of state changes and a bunch of transitions. And each of the transitions says, well, if certain conditions hold in the global model state, so it reads the model state and says, well, if something's happened, the temperature's too high, whatever can happen in a production system, then the transition generates another event. And so you always sort of have a bunch of active events. They get processed and they spawn off new events, and you do this sort of until the end of time. What you can't see in this picture, but what we'll see in the model is that the events also have relative priority. So they always happen in a certain order when they do happen. So, yeah, I guess, so that's it. And so my plan is to show you the Java code and to already get you thinking, how would you do this in Haskell? And not just how you would do it, but also how would you explain a Java person how you know how to do this, right? And can you explain it without resorting to like 10 years of Haskell experience, which certainly wasn't needed in order to create the Java code, okay? So that's the plan. So I'm going to fire up my trusty old Visual Studio, if I can find it. So that's going to be a theme here that Zoom makes it difficult to find. Here it is, I think. So now you should see it. So this is all code that is checked into the GitHub repository also. I think there's a directory called Java or Java code or something like that, right? And so basically, so I'm just going to present it to you as, the people from Oliver Rose's group at the Bundeswehr-Universität presented it to me. And they said, here's a bunch of Java code. And you can see here a bunch of packages. One says meta model, whatever that is. There's a model library, simulator, start something, and a bunch of individual files that start a simulation. So I just want to go through it in sort of a naive fashion. Again, ask questions if anything is unclear. So what I did when I read this code, I said, well, I'm just going to look, since it's about discrete event simulation, I'm just going to look for something called an event. And sure enough, there's a class here called the event class. And so as you can see, it's not very complicated Java code. So it says, so an event has a name here. Has a name, it has a priority, which will control the ordering of the events as they get processed. And as I mentioned, each event comes with a list of transitions and a list of state changes. So state changes are changes to the model state, and transitions are possibly spawning off more events as this event gets processed, right? And then, well, you can see the typical old-fashioned Java pattern here. So you write a constructor. The constructor mainly initializes the object with the name that you see here. But everywhere else with the priority, the transitions, and the state changes, these are left empty. And then there are various methods that allow you to manipulate the transitions and the state changes. So you can add a transition and you can add a state change. Okay.
There's a question on the Zoom chat.
Oh no!
Yeah. Is this a synchronous event model? I.e., each event can create more than one event.
So I'm not sure if these seem to be to me two questions. No, I think Yeah, so it's a very good question as to the design of sort of simulation systems. So it's not in the, so events, Gabor, so mentioned this. So the discrete event simulation, the events always happen in sequence, whereas in synchronous event models, often in sort of typical synchronous event formalisms, you can have multiple things happen simultaneously, and the model actually models it accurately. But in this world where you are dealing with production systems and with discrete event simulation, the events are always happening sequentially, which of course, in my mind, is problematic because it's supposed to model a real world system, and the real world system, of course, you have things happen concurrently. And here there's this idea that somehow magically these events, according to the priority, sort themselves into an order, but that's how it is. Okay, so hopefully, Gabor, I've answered that. Otherwise, just follow up. So yeah, so various caveats associated with this code, right? So there's the event. Then I mentioned, so when you look at the event, you can see that there's a state change is associated with an event, so we can look at that. Well, a state change is an interface, and it just has this method that says, where something called the model state gets passed in. So we're going to have to look at what the model state is, and it has this return value that we all love when we see it in Haskell. It has void. So change state can do absolutely anything that you want, but the idea is that it will operate on the model state, okay, and mutate it in some way. So, and well, why don't we just follow that and say, well, what's the model state? And the model state, you can see, is a map from strings. So it's a key value store from strings to objects. So you can have various aspects to the model state. Each aspect has a name, and you can associate any value that you want. And this is not the subject of the tutorial, but right there is an issue with Haskell because, of course, we don't have an object type. We're going to have to put something more concrete or more abstract there. So that's the model state. What else do we have? Then we said, okay, an event, it comes with state changes. Okay, we covered that, and also comes with transitions. So what's a transition? Well, transition, it has, so a transition, remember, is something that might spawn another event from the event that we're at. So it has a target event, it has a condition. So essentially what happens is that you have an event that has multiple transitions associated with it. Each transition has a condition, and only those where the condition returns true, whatever that is, will actually fire and cause the target event to be generated. And there might also be some delay involved in here. So we're going to have to figure out we know what an event is. We have to figure out what a condition is, and we are going to have to figure out what a delay is. And otherwise, this is the transition is very simple. It's just a holder for this data. It doesn't actually do anything. So here is a delay. So delay, well, you can call it and says, well, that event that gets spawned, it's going to get spawned, but it will happen later. And the delay is just a number that says how much later it will happen. And as you can see, it has 0 arguments. So probably it's going to have to access some state in some sense if it's not going to always return the same number. And the next thing was the condition that determined whether an event should be generated, whether a transition fires. Well, the condition, also only has a single method that returns true or false and is supposed to operate on the model state. But of course, again, this being Java, it can have any effects that you want. Okay, so any questions so far? Let me look in the chat. Let me make sure. Okay. If not, you can always unmute yourself and make things more lively. So, well, then I looked at model examples. We've covered model state. So I looked at this and I said, oh, this implements something called model. So we're going to have to find that. We haven't looked at that yet. A model, well, is something that has a name. I don't think it's used anywhere. And it's sort of, the model just starts from an initial event that you see here, right? That's it. And you can see here, models that say, oh, okay, we're going to build the model. and you can see a model is built by creating a bunch of events, saying that there's various state changes, but you can already see that it refers to classes that we haven't looked at yet. But you can see that it sort of constructs a bunch of events, and those events are then sort of networked into the actual state machine that is the discrete event simulation. Well, we're going to have to look at, so for example, it says here set value state change. Well, there's a class here that does that. That implements a state change. And remember, a state change is something that is supposed to operate on the model state. And well, set values namestate simply says, well, that name is going to be, remember that the model was just a bunch of keys and values. This just has the name of the key and the value. For some reason, I don't know why, here the value, which was object before, is here a long value. So you can create one of those things and have it set to a value. And you can see here when you here's that method from the interface, and when you call it, it accesses the model state. It accesses the table that contains the keys and the values and puts this new key and value association into the model state. And and it goes on like this. So what else? So for example, here's an increment value state change that, as you can guess, well, it has an increment here, and it doesn't just set a value, it extracts the value. It needs to be a number, and increments that value by a certain increment. Oh, what happened here? Sorry. So those are the state changes. Then there are conditions. So for example, here's a true condition, always returns true. Well, that's easy. There's also a larger than value condition. I think you're seeing the pattern here. It says, well, if you look in the model state, then the value of that name needs to be larger than that value, then I'll return true, otherwise not. And what else do we have? We have a bunch of delays. So here's a constant delay. That just returns a certain constant number. There's a zero delay, which always returns zero. And then there's, interestingly, something called an exponential delay. And the exponential delay, well, uses a random number generator. And as you can imagine, the random number generator generating a random number is an effect. So that's going to be interesting for modeling that with the help of some kind of effect system thing that we maybe have available in Haskell. There's also a report generator that then sort of collects everything that happens in the event simulator and writes out a report that, as you can see, is not terribly interesting. It's mainly concerned with text and table formats and things like that. So we're not going to have a closer look at that. So those are sort of the building blocks that we have for the event simulator, and the simulator core here sort of puts those things together. So we could look, for example, at something called the main program, and it has, a little bit more space. So here's something called run simulation, which takes a model, well, which says, well, we're not going to simulate until the end of time. We're just going to say when the time reaches, a certain value, then we're just going to stop. And you can see that, well, this main program, it manages a model, it manages a model state, it manages an event list. So we're going to have to look at what that is, where it manages a clock, and it manages one of these report generators, right? You can see here that there's something called, tellingly, an initialization routine for the report generator, never mind. And then what it does, it has this while loop here that looks at the current time, as long as it's less than the end of time, and as long as there are events in the event list. So we're going to have to check out what that is. Well, we're going to get an event from the event list. We're going to process that event, and then we'll just see if we'll just do the whole thing over and over again. So so I think we're going to need to look at the event list. So that is this job here, which says, so as I said earlier, or Gabo asked about this, the events happen in sequence, and they happen in a sequence that's determined by the event's priority. So, well, there's a special class here that manages this. And as you can see here, whenever an event is removed, so the idea is that this is always sorted by the priority, and it always gets resorted when an event gets removed for some reason. So, and then there's a toString method, not terribly interesting. What is interesting maybe is that, well, the event list doesn't store events, it stores event instances, events that happened at a certain time that we're going to need to sort of manage the proper order of events. So here's an event instance, it just has an event and the time when it is going to fire. And you can see here that when we have two events, we can compare, or when we have two event instances, they first of all get compared by the time at which they fire, and when the tiebreaker for that is the priority. So if two events happen at the same time, well, they don't actually happen at the same time. They happen in an order that is determined by the priority. And then there's also the clock. Well, the clock just manages a number that advances, and so we go back to the main program. Well, here's an event. Here is, so remember that the central loop called a timing routine. The timing routine removes an event from the event list. Here's the event instance. It sets the current time to, it sets the current time in whatever time that event happens at, because there's nothing happening until then, and returns that result. And the central loop then feeds that to another method called the event routine. The event routine iterates over the state changes, executes all the state changes. It updates various statistical counters that are relevant for the reporting. And then it goes over the transitions, checks for each transition if its condition is true. And if so, it adds events to the event list, right? Creating new event instances. Okay, so far? So that's your Java program, right? And as you can see, it has a lot of code that has side effects, that operates, on the event list, that operates on the, there's a random number generator sitting somewhere. It operates on the model of the simulator and so on. But it's fairly straightforward code. It's not hard to understand in Java. There are no deep architectural issues at this point. Any questions so far?
It looks a bit fishy that the for loop for the transitions doesn't stop after finding the first transition that is applicable. And it seems to kind of run several transitions.
Yeah, it might run several, right? That's the way this thing works. So that's actually intended behavior, right? Okay. That several transitions might happen, right? An event might spawn several further events from there.
Okay.
So, but I mean, we could, I get, there's various ways where you could argue with that code and say, well, there's ways in which it could be improved, and it certainly could. And as I mentioned, right, this whole idea of discrete event simulation, or this particular implementation of it, is rather arbitrary. So it was my intention to really take it as it is and not sort of grapple with the domain modeling that's behind that, and just say, well, if you're happy doing this in Java, then the basic assumption is that you should also be happy doing this in Haskell. But how do you do it is the question, right? And so anyway, so there's the Java code, and so now I'm going to switch one more time to the slides to a certain point. See if I can find them. I think they're here. So I'm really concerned with so when translating this into Haskell, right? I mean, one solution would be, I asked a couple of people who are professional Haskell programmers. I said, how do I do this, right? And they said, use IO, right? So we could just do the same thing that the Java code does, and just tap into that big stream of goop that is happening underneath the program. But my concern was to do it better than the Java program, and to restrict the effects, and to really make sure that the different parts of the program document what kinds of effects they have, so that you can't have the various bits and pieces of your event simulator tap into some data that has nothing to do with the model, for example, right? Also, I wanted to be able to compose different effects modularly. And what that means in particular, and I think we'll see that, is that I wanted to be able to sort of write the program, by sort of, if I follow along the Java program, right, and translate each piece into Haskell, I would rather not have to reach a point where I'm sort of at the halfway point, and the next bit then says, oh, you have to go back now to your to the beginning of the program and rewrite everything that you did, because that's kind of what happens. So we'll get there. But that's not my idea of modular programming. Is that you've programmed how your code deals with events, for example, but then you can't extend that code easily to the point where you can use it in the context of an entire simulation. You have to go back and rewrite some of that to do that well. Also, a separate concern is not so much with this code, but generally is that I would like to separate the interface of effects from the implementation. When we do big projects, one of the concerns is always that the effectful computations are sometimes hard to reproduce when you're doing tests. So typical effect might be, access, be your big database that you have somewhere, for example, and for testing, you often don't want to connect to the big database, but instead you would like to sort of mock it or replace it by some sort of simulation of the database and so on. But we'll see that this is something that some of those solutions in Haskell actually do, and we'll see how that works. And what's not a concern, which is why it's in parentheses, is that sometimes you want to have effects that are defined in terms of other effects, but I think that would just be too much for this tutorial, and you can get away with quite a bit without doing that. So there's that. Okay, I'm just peeking at the next slide to see where that goes. Any questions so far, or any suggestions on how I should proceed? Okay, good. So, well, I mentioned that I'm only a casual Haskell programmer, but in fact, I did quite a bit of Haskell programming in the mid-90s. And well, lots of you probably weren't born then, but in the mid-90s or in the early 90s was when monads came up, and they were getting popularized by the mid-90s as a solution, or as a means to express programs that contain effects, right? And so the obvious thing that you have, well, I'm sure that you all know this, right? In Haskell, when you have effects, you should really do this using monads. So I'm going to switch now to back to my project, to the Visual Studio Code. Here it is, in principle, and well, that's just still displaying the Java code, and I'm going to switch to the live directory. So I set up in the code, I set up two directories. One is called live, and the other one is called prep. So prep has all the code and it's all finished, and live has a couple of bits and pieces missing. In particular, you can see here that the monadic code. So there's a file just called monad.hs. So in a directory called zerts, DES, discrete event simulators, and then there's different versions now of the event simulator using different approaches to controlling your effects. And some of them are just mostly empty or partially empty, so that we can actually develop them as we go along. And I'm going to hopefully push to GitHub regularly, or you can just look at the finished version, just to make sure that I don't just skip over important parts. So, well, so as I said, the report generator is not going to be a primary concern here. So the report generator is sort of just in that file already. And so the first thing, well, you remember that the model state was, so I kind of started, well, events are some things that operate on the model state. So the first thing that we should do is create a data definition for the model state. And obviously we can use the original Java program used a map, so we can just do the same thing in Haskell. The only problem is that the Java code used a map from string to object, if you remember, and it's not quite clear. You might want to have discrete event simulation. You might want to do that with different types, different from object. So and the way to do that is you put a type parameter in and see where it leads you if you don't know what that type is yet. So I'm just going to call that type V. So V is values in the model state. I did this a couple of years ago. I've learned since then that I should probably depart from the Haskell tradition and just use longer names. But so it is. So this code is a couple of years old. So I'm just defining that as a type alias. Well, so the question is then, how does, so we saw a bunch of pieces of code that manipulate the model state. So for example, there might be a state change, and the state change is supposed to change the model state. So it might read the model state, it might we had this increment thing that would read and write to it. And so here is where we go and say, well, this is an obvious application for a monad. So I'm going to call, so as we know, in Haskell, when we have something that's effectful, we give it its own type. And I'm just going to call that type model action. And model action, since it operates on the model state, is going to have the same type parameter. And so I'm just going to, and I'm going to use the state monad. And the state monad is just going to contain a state of type model state of V. So, by the way, as I do this, if you say, oh, Mike, why did you do it? You're doing it all wrong. Please jump in, because as we'll see, I'm doing it all wrong. So, and then we can go and say, well, we can write various functions that are monadic to access the model state. So I could write a function, for example, get model state, and that says, that's going to be a model action V, and it's going to return that model state, right? And get model state is just going to be state get. So that's very boring, and so on. So we can define the various operations that are the equivalents of the code in the Java code. So we could do something like this, right? Get value, which where we give it a key and we ask it to return the corresponding value. This is not me typing. This is Visual Studio. And get value name. And the code is very pedestrian that I'm writing, mainly to match the Java code, right? So the model state is just, well, we could actually write get model state. And, we could say map lookup, name of this. And of course, there's this pesky Haskell tradition of totality, but I'm just going to ignore that. Right. So, and just pretend that, our event model always only looks up states that exist and return this, right?
There's an equals missing.
Yes, very good. Thank you. Just testing if you're actually reading along. Good, and so on, right? I'm just going to sort of selectively copy a bunch of code. So for example, if we wanted to remember that code where we incremented a value that might benefit from an abstraction called modify value, which just accepts a function that maps a value to another value, and we just then create a corresponding state modification. Now, well, the next thing that we had, remember, is, okay, so this is the model state. Then we had events, and in order to do events, we need to define what conditions are and what state changes are, right? And so, so for example, a condition. And remember, a condition was also something that operated on the model state. So kind of as we write it, we kind of have to go like this. Well, we want this to be a function of the model state and return a bool. And of course, GHC complains because model state needs a type parameter. And so we need to propagate that type parameter sort of up the type hierarchy, right? So that's a condition. And then we could remember there was this thing called a true condition, which is condition for any type V, if and a condition is just a function, and in this case it always returns true. Okay, and remember this bulky thing. I'm just going to, well, let me just copy that. I think remember this bulky Java class that said larger than value condition. Again, not the most elegant way of doing that, but here's the exact equivalent of that. So larger than value condition is something that takes a name and a value, and a model state, and well, looks up that entry in the model state and checks whether the value there is greater than the value that we specified. Again, ignoring the totality aspects that are here. I'm really just trying to create a version of the Java program and focus on the state. So now, okay, so that works. So the condition is supposed to be is this function of the model state, so that's fine. Now remember that there was not just a condition associated with each transition, but there was also a delay associated with each transition, right? And what was this delay thing? Well, delay was something, if you remember the Java code, it did not get a model state for some reason. I'm sure it makes sense somewhere. But what it did do, there was this thing, this exponential thing that had access to a random value generator. And so the naive way of doing that is to say, well, delay is just something that is in the random monad and returns an integer. I'll not import this. I think this is, I had a type alias in here that said random is random standard gem. So then that should go away. So that says, okay, so a delay is something that might access the random monad and return some integer, right? And then we can do something like exponential delay, which well, we feed in some double number, feed it a little delay. This just happens to be similar to the Java version. We give it a mean value, and we say, well, some random value. We do this. We call get random and return. You know, and I just copied the formula from the Java code, so that was great. That all of the math functions that I needed were available, and so on, right? And so I can have, remember, there were these very simple delays, you know, 0 and constant, and we can just have them be very simple functions in the monad. Okay. So there's that. Any questions so far, or any doubts about what I'm doing? Right? Maybe you can already see where it's going, right? Where it's going to be problematic. Now, of course, we need. We can now, with the help of well, we have. Remember that we had events containing transitions, so we could do that, and we could. Whoops! What happened? Ah! What button did I press? The wrong one here. Help! No, it's not getting better. Ah, okay, good. So return. So anyway, so an event is, right, we're going to make that. Now we can already, if you remember the Java type, well, it was something that had a name. So, and it had like 4 things in it. And at that point, it's reasonable to make a record type. It had a priority. You know, that was an int. It had a bunch of transitions, and we can just make that a list of transitions. And well, you can already see where this is going. State changes, and that's a that's something here. And so, well, maybe we need to define a type for state change, which is just a model action of v that returns nothing. And you can see this pesky thing. We need to thread the v through all the types here, right? So so we need to do this, right? And it says, oh, you haven't defined transition yet. And of course, well, maybe not of course, but these 2 types are mutually recursive. So we have transition, and we can now see, okay, we just have to thread the v everywhere. And so event v, so, and condition v, and there's this delay associated, which thankfully doesn't have a v associated with it. Okay, so now we have sort of the individual building blocks that are needed for our discrete event simulator. We have events, we have transitions, we have conditions, we have state changes, and we've defined that in a monadic framework, just as one would expect, right? And now and now we could actually go and construct an actual model, which you see in the prep code. Now, the next thing that we need to do is, well, we need to build on that in order not just to look at individual events, but to look at the entire simulation and the entire simulation state. And if you remember, there was this main program which had that in the Java code. I'm just going to give it a slightly better name. So there's going to be a simulation state, and well, so what is in the simulation state? Well, so there is, I call it S-state to get proper names for the accessors. I've heard that that is to change for the better in Haskell in the near future. So there was the clock, right? There was also, well, I thought we can do a little bit better than the Java code. The Java code would always resort the list of events every single time something was removed, but we can use a data structure called the heap, and functionally, and fortunately, that's a functional data structure of event instances. And we're going to have to define what an event instance is. And then we have to have a report. Well, so there's that. That's sort of the essence of what was sitting in that Java class, right? We need the clock, we need the open events, we need the report here, and okay, and we can already, well, clock is undefined. We're going to just make a new type here, clock, to model sort of the make it very similar to whatever show, something like that. So that defines show. And of course, we're also going to need to define what an event instance is. Well, so remember that, you can already, it carries, so an event instance was just an event with a timestamp when it happens. And of course, we again need to thread the V through. And of course, the same thing holds here. So the V needs to be threaded through everything. So that's the simulation state. And so any questions so far? Maybe. Okay. So we have this, right? So I kind of try to, write the code only trying to think locally, right? So at this point, I might say, okay, it's called the simulation state. How will we manage the state of the entire simulation? Well, we're just going to manage it by a state monad of the simulation state. Now, the problem, of course, is that there's a couple of things missing from this, and that is the model state, for example, is not there, right? And so already we have this problem in that the model state upstairs, we defined that the model state would be managed by the model action monad. But of course, we're going to have to manage that throughout the entire simulation as well. So right here, we have to say, well, in addition to these sort of global aspects of the simulation state, we're also going to carry the model state here and put that in here, right? And so here's the first problem, right? First problem, can't have this managed by model action as monads don't compose, right? We can't have two monads that represent two different effects and then try to put them together. That just doesn't work. And if we do this, one of the problems that hasn't manifested itself yet is the fact that there is a random number generator is also involved in this. So we can't even use our model action in order to manage that random number generator. So we also need to manage as an aspect of the simulation state the random number generator. And fortunately, sort of the Haskell library allows us, luckily, I should say, luckily, the Haskell library allows extracting this. So the random monad is essentially just a state monad, and the Haskell library allows us to extract that state and feed it back in, and therefore carry the random number computation through the entire simulation. So this is the problem with monads, right? Is we're defining if we want to do that in a modular fashion. In one part of the program, we say, oh, okay, events deal with two things. They deal with they deal with managing the model state up here, and then later we discover that events also indirectly deal with random numbers, and we haven't even noticed, or at least when I was writing it, maybe I wasn't looking too closely, I didn't even notice that these things could never work together, right? In fact, or without some fancy manipulation that happens somewhere. So we can't just easily combine the random monad, the model action monad, and the state monad for the simulation state. Instead, we have to go through various gymnastics in order to do that. Okay. Okay, so far? So monads don't work for sort of fine-grained control over your effects, right? So that's maybe the first insight. So far, maybe somebody can say something or ask a question. I don't know if you're all like at a super high Haskell level, and this is really really easy or trivial for you, or if I'm saying something interesting. I don't know. Just gonna wait 15 seconds.
Can I add something?
Yeah, please.
I might be mistaken, but if I understand correctly, also committing to using the IO monad as you were suggested when you were talking over the slides, also could potentially bring various unwanted effects. For example, if we use IO monad, we cannot tell by the type signature that this particular function uses only the subset of effects which we know how to handle.
Yeah, very good point. Yeah. So I guess I could have programmed it also using IO, right? That's what my colleague, my fellow Haskell programmer, professional Haskell programmer suggested a couple years ago. He said, just do it in IO. And in fact, I could. So because the GHC IO monad also has state, it has mutable references, and it also has random numbers, right? And so I could easily just put it in the IO monad. But the problem is then the effects are no longer controlled, right? Because not only has IO state and random, it has all kinds of other effects. And we don't know from the type of a program, if it just says IO of something, we don't know from the type of the program what effects it will actually use. And so that means that, you know, we can do anything here. And so that was, but that's why I did not follow this particular route as going through IO. In fact, there is, Krasrov, there's something called the reader T monad, or the reader T pattern, I think it's called, which suggests that really for state management, for configuration management, things like that, your application, you should really use IO and carry all the references in a reader monad that's wrapped around the state monad, right? And I think that's a pragmatic solution, and it works for assembling your application. But the problem is, again, that your monads are no longer controlled. Especially with an eye towards sort of teaching people the basics of software functional architecture, it was really important to me that, I mean, it seems that Haskell's been around long enough that one should expect there to be a solution to this problem of actually controlling the effects in a pure functional language. I don't know if you feel differently, but and I was absolutely sure 3 or 4 years ago when I started this, I was absolutely sure that there would be an easy solution to that. So, I mean, what I did back then was, so I felt, okay, so clearly there's just, I mean, the problem is, you know, as with anything else, right, is we just have these building blocks and we have no way of combining the building blocks. And that means in the case of monads, they're just kind of the wrong kind of building block. so I should really just use the right kind for that, right? And the same discussion I remember came up in the 90s when we said, well, the problem is always when you want to have a different set of effects, you have to change your monads. You don't necessarily need to change all your code, but you need to change your monad, and you change your monad in such a way that you put all the effects in there. So that would be the next thing, would be next step, right? Would be sort of one big monad that has all the effects that I need. But again, this has the problem that it's not modular, right? We can't, thinking about events, we're not, or at least I wasn't thinking about the simulation as a whole yet. And that would have meant, going back and changing everything that I'd done before. And also it would have meant that, again, you have events that have access to aspects that have access to effects that they shouldn't have access to, right? The lowly little event should not have access to the state of the entire simulation. For example, if that were true, the event could on its own modify the event list or change the clock and turn the clock backwards or do something else that's evil. And so it's not modular, and again, you lose some control. And so the question is then how, obviously just telling people use monads is not the right approach for this problem. At that point, I was already getting worried because I remember, and I'm sure you've experienced this when you explain monads to other people, there's already a significant barrier to understanding monads, and obviously, and monads are not enough. And so in the 90s, I think it was Mark Jones and Paul Hudak and his coworkers who said, oh, okay, well, obviously the problem is that we don't have enough abstraction in the program, and maybe this whole problem can be solved by abstraction. So, and they came up with an idea called a monad transformer. So, well, how does that work? Well, the idea is that you define individual effects, not as monads, but as functions that add that effect to an existing monad, right? And this way, you could sort of start with a trivial monad underneath and sort of apply monad transformers to it. And each time you apply a monad transformer, you sort of add one more effect that is available to you. And so it looks kind of like this. So I have to switch the share if I can find it. Feel free while I look for my PowerPoint to ask questions or jump in. So this is what monad transformers look like. So typically at the bottom, you have something called identity or IO, actually. And you kind of wrap further effects around it. It took a little while. So last thing I tried to explain was that you might ask, why is there this onion model? Why is it monads wrapped around other monads? Why can't you just have a set of effects? The same way that I think, maybe people programming in Java think about it. You have this effect and that effect and that effect, and they're all sort of not very closely connected to each other. And the reason for that is that some effects are control effects, such as exceptions or continuations, or something like that. And for those, the ordering matters. So if you resume a continuation, for example, one of the obvious questions is if it goes back in time to the previous state or not. And that is exactly the difference in layering, in the order of the layering. Okay. So anyway, as you do this, so let me find my Zoom. We'll go back to the code. And if I can find it here. Here it is. So here's the code. So I just switched to a different file here, monad transformer, and it's just as empty as the previous one is. And maybe we should make it so that we split into two rows here and have the old code here. So here's the old code. So So, and remember, here was the first monad, kind of, right? Here, right? In that, I'm just going to copy the model state. Right. So here was that first monad that we had, and the so when when we program in a way where we already know that our program is going to have several effects, and maybe we can know this, right? We'll have effects other than just the model action, and if we remember that fact, then we can say, well, we're not going to define a monad, we're going to define a monad transformer, and a monad transformer is just something that has a type parameter for sort of the monad that is underneath in the onion that you have, right? And unfortunately, sort of the monadic libraries that come with Haskell all have, they don't just have the state monad, they have the state monad transformer. So we can just do this, right? So we just do something, we just do abstractions, right? In the purest sense, in that we abstract over these things. And then, so that means already that we can wrap the model action around another monad. And in particular, what we can do is we can, let me just sort of copy some code. So the beauty is that we don't actually need to change all that much code. So we can have get model state. Well, can't infer a type, right? But get model state now has this type. Well, we can't just say, model action, before, let me get the old type here that we can modify it, right? So here's the old type. That obviously doesn't work anymore. Here is the sorry, we need to write it here. So here, obviously we need to put that monad in. Well, what is that monad? It says state plot get. What is the problem? Well, it says there's no instance. It doesn't know that monad is a monad yet. So we need to put that in here, right? So all the types get more complicated, right? And even with simple things such as this one. And that's something that I want you to keep in mind as I think monad transformers are still a common approach for controlling your effects. It's not just can you get it to work, because you can get it to work, but is it can you explain it to somebody else, right? And fortunately here we can actually get a nice type here that that gets inferred. I'm just going to replace that by a v, so that's nice. And so we can kind of go through the program and copy code and adjust it, right? And what's great is we can also take the random, the code that has to do with the delays, which remember needs access to, what is the problem here? Modify value. I think that also needs a type. Well, what is this, right? It has a string, it has a v arrow v. So it takes a function, and then we want to have a model action t of v, some monad, and it returns nothing. And then I think it's going to complain again that it needs a monad constraint. Yeah, so there we go. Okay. So anyway, so it, and we can go on like this, and we kind of course, we could also use the a monad transformer for the random, but the random is something that we can just wrap inside the model action t. So I was too lazy to actually do that. So a lot of the code that comes from here, that is down from here, actually works the same way as it did before. So let me see where we are. Of course, I'm looking at my notes. So we have delays, we have this, and well, so what are we going to do? Well, so a state change, right? This thing here, that is, one of the components for an event, right, of course, also needs to have a model action V, needs to have the monad here. And so you can see that similarly to the V, right, the monad, so you're threading a monad parameter through your program, right? And so here's the stage. Oops, no, what happened? Where did I go? So back here. Oh no, the marketplace wants to sell me something. Okay, so far? So really, this needs to be a state change T now. So everything that was a monad before now turns into a monad transformer. And so, well, and we're going to have to make the requisite changes, right? So if I go here, event V, well, so we can right now, we can see here that, well, so the state changes, well, we can't just say state change anymore. We have to say state change V monad. Okay, and that also means that we're going to have to put the monad parameter in here, right? And it goes on from there. So we go, here's the transition type. How does that work out? And then it says, oh no, monad, V event needs a monad parameter. So this thing needs a monad parameter. And of course, then this needs a monad parameter. And then things kind of work out, right? So that's the step. So I was already feeling not very good about this because, I had to go back at this point and rewrite all the monadic code that I had before. But if we just teach this paradigm or explain this paradigm that if you have an effect, you just represent that effect by a monad transformer, then I figured, okay, this can work. And this way, I could now go and say, here is a more reasonable definition of simulation state where I only have the things that are not managed by the model action that are in there. Okay, so again, event instance, everything acquires a monad parameter now. I'm just going to call it M now, which is the case in the original code too. Okay, so far. So this is the idea that came up in the 90s, right? Is that we would just instead of having monads represent effects or bundles of effects, we just use monad transformers and assemble our monad using these transformers. And this originally came up in papers that had to do with modular interpreters, and I thought that was great at the time. It was very, very influential in many ways. Now, ultimately, let's see how far we need to go. Oops. Zoom was playing tricks on me. Now here's one problem is, well, let me not spend too much time on it maybe, so that we can get a little bit more relevant stuff in here. So now the problem is that, well, we can define one big monad to manage the simulation, and we already know, so if we have something, we can have something like this, right? Simulation V, and again, we abstract over the monad, and that is a state T of the simulation state V of M, and then we wrap that around the model action T of V and M, right? And typically, here the M is the random monad. Actually, but we've abstracted over that. So in principle, the delay could have access, I don't know, to the weather or to environmental condition in the production facility or something like that, right? So this kind of works out now. Now, so we have event instances. So one of the problems is now that, well, you have this structure here and that you have three monads, you have two monad transformers in one monad. But of course, if you, for example, wanted to, the problem is that these things are not equal. So if you have an effect, for example, in the model action T monad, it is not automatically, problem is, an action, an effect in model action T VM is not an effect in simulation VM, right? So but what we can do is we can lift it, but we can lift it with an operation we can lift it with a function called, lift, right? And lift is sort of the defining function of the monad transformer type class that is there, right? And so now we can combine effects, but we have to remember that when we actually combine effects at different layers of the monad, we have to make sure that we lift them the right number of levels. So have to lift the right number of levels. And if you look in the code and prep, you can see that it's actually possible to then assemble your program this way, but it's super awkward. And also you can remember, you have to remember how many levels there are. So if you change the onion structure of your monad, so the number of lifts is sensitive to the structure of your monad, right? And if you change that structure, then again, you have to go through your program and make a lot of changes and adjust the number of lifts. And if you look in that code, you can see multiple lifts. Okay, so far? Any questions? Okay. So then so that was kind of that was what I knew from the 90s when I got back into Haskell. Yeah.
I was talking and my mic was muted. Can I ask a question about monad transformers? I know that in languages like Scala, for example, monad transformers are not a desirable solution because they cause a lot of extra allocations. And so in Scala, things like zero began to be more popular because of this reduced runtime cost. Is it true in case of Haskell's monad transformers? Do they also cause these extra allocations due to boxing and unboxing types?
They do, but GHC is often able to do quite well. I think better than the Scala compiler, right? And also ZIO. So I know very little about Scala, but from what I know about ZIO and the way things are in Scala, so the way it's been explained to me, monad transformers. Yeah, so anyway, so in ZIO, the problem is that there's only one monad, which is the ZIO monad, right? And you you sort of work the other way around. Here, what you do is you build monads from small features and you add features and you make it bigger and bigger. Whereas with ZIO, you have this big monad that has lots of stuff in it that has like concurrency and IO and whatnot. And you restrict access to features to ZIO in order to control your effects, right? And that works as long as all the features that you need are in the ZIO monad. And as soon as you need features that are not in there, that approach breaks down. Does that make sense?
Thank you.
Right? Again, correct me if I'm wrong. I know very little. I've never used ZIO. But there's been one innovation because this adjusting the number of lifts is so tedious. You can find another package in Haskell called the MTL package. And MTL, monad transformer library or something like that, the idea here is that instead of saying I have a concrete monadic structure in terms of monad transformers, I'm just going to say, well, my monad has a bunch of features, and I'm going to encode these features in terms of type classes. And then later, I will connect my concrete implementation of my concrete monadic structure to the type classes with appropriate instances. So and this is how that works. And so remember, I had that one concern that is relevant, not particularly relevant here, but in other projects, and that I wanted to separate implementation from interface. And that's what MTL does. It says, instead of talking about concrete operations and concrete monads, you just say, well, a monad, here you can say ModelState as before, any monad can manage, can be a model action monad. That's what that says. Any monad can be a model action monad as long as it supports these three operations, right? One operation says current model state, returns the current model state. One modifies a value within the current model state. And one of them is to eval a condition that depends on the model state by passing a function. So these three things, any monad, as long as it implements these three operations, can be a model action monad, right? And then again, you can define an implementation in terms of the monad transformers that we've already seen. And then you connect these two things. You say, well, we said, with the monad transformers, we said, the model action monad transformer is just a state monad. And we can now explain, well, a state monad that manages model state can implement these operations, this way, right? So the current model state operations, here in this type class instance, state.get. So these are just the exact implementations that we had before. And then there's a neat trick that MTL does. We remember the problem was that we always had to think of the number of lifts that we need with the monad transformers. And here's a trick around that just says, well, if you have a model action monad here, and you wrap a monad transformer T around that, right? So you put another layer around the onion, then the whole onion is also a model action monad, because we provide implementations in terms of lifting the one from the lower level one level up. Okay, and the way that, well, if you need the undesirable type instances extension to GHC, but then GHC will automatically figure out how many lifts you need in order to have your effect in the entire monad. So that's great. So that's very convenient. And you kind of think, okay, that's wonderful. I can just keep writing my code. And so here's this model action monad constraint now. Again, keep in the back of your mind, what do you need to explain in order to make this accessible to anybody? You can see here the event representation just adds a constraint and says, oh, this mysterious monad that we're abstracting over needs to be able to handle model actions. Okay, that's fine. And you have this constraint here to define your model. All that is fine. You can define your simulation state, and then you have your simulation state monad. And by wrapping that around the model action monad, you automatically get all the actions from the model action, and you no longer have to write any lifts. So for example, here you can see that generate events function. I think these functions, what they actually do is not terribly relevant, but you can see here that it is within the simulation state monad, and it runs an effect that is in the model action monad. So we have this monad here that is two things. It's a model action monad, it's a simulation state monad. And here we can just eval the condition. And if you look in the prep version, that actually needs one or two lifts in the original version. And here we don't need to put the lifts there because GHC figures them out automatically, one might think. And so, all these concrete monad constructions now turn into just constraints where you just say, well, this happens in any monad you want as long as it implements these operations. And you can then provide this run simulation function, which says, oh, okay, well, only here do you provide an implementation and say, well, any for the state monad that manages a simulation state, manages a model state, manages something underneath, we can run the whole thing with the appropriate functions from the monad transformer library, and things are fine. So you've noticed at this point that, again, I've rewritten the code slightly, but it got nicer compared to the monad transformer version. The problem is then run simulation is then calling it, right? And so here's the version, for example, from the monad transformer library, right? So in principle, that should just work, right? But unfortunately, it says, oh, here's a problem. And it says, couldn't match type, rand T, standard gen identity. Maybe we should switch to the, well, it has to be enough, I think. Hopefully you can see that. Couldn't match, this one, rand T standard gen identity with stage C, where the standard, so it tries to equate the entire onion with the inner part of the onion. for some reason, and arises, and that has to do with just the way that the inference works for type classes. And I don't want to spend too much time on it, but I tried for a while and I couldn't make it work. So I couldn't make it work at all. I could not produce a program that would actually run the simulation that would type check. And so I thought, this is terrible, right? As you write your program, you write a bunch of code and all type checks. And we all know in Haskell that once it type checks, it runs, right? But unfortunately, I couldn't write the main function that actually calls it, because that wouldn't type check, and I couldn't find any way of doing that. And so I welcome you to try and make it work out. I mean, one obvious problem, I think, as you can see, is if you have MTL with this automatic lifting that you have, it can only work because lifting says you can lift, the operations, for example, of your model action monad. It can lift those through the through any other monad that you have. But of course, if you think of the monads that are in the standard library, so the state monad, for example, the problem is that the MTL comes with instances of this of monad of this for all combinations of the various monad transformers in the standard library. So you can combine a state with a reader, and a reader with a writer, and a writer with a state, and so on. Unfortunately, you can't lift a state through a state, right? Because then the type inference doesn't know what level, the state at which level we're actually talking about. So there's already an inherent problem here. And also there's the problem, of course, if you want to do this, is that you have a quadratic number of instances that you need to write in order to explain how to lift each monad through each monad transformer, right? So so that is so MTL was just completely unworkable to create a realistic software architecture, and I was stuck. So I think that was terrible. I was sure that it would turn out nicer than that. So that's where we are at, I think, is that, or where I was at a couple of years ago, that all the solutions I could find on how to express stateful programs or stateful software architecture such that it would allow me to control my effects is just terrible. Either I couldn't make them work at all, or in the case of monad transformers, just I don't know if you can sort of think back to your childhood when you were just learning about monads and how your head kind of blew up because the concept was so abstract, and then monad transformers are one level of abstraction up from there. So how do you handle all of those things? So I think these are completely unworkable to explain to people coming from Java as a suitable solution to implement the things that they do routinely, right? This is all a no-brainer in Java, right? And so fortunately, the landscape has changed since then, and there are lots of libraries available that allow us to do much better, with some caveats, however. So so this is the point in
taking that much time.
We were in the break, and it was definitely related. So I think we're back anyway. So, and I think actually these things seem unrelated, but maybe we can see a connection after the next thing I want to talk about, namely that I think the fundamental thing that happened and took a while to actually materialize in the form of actually workable libraries was the idea of a free monad that you might have heard. And so I'm going to try and explain that. And the way I think to understand free monads is to think, well, remember that we said, or that I said, well, one of the concerns is to separate implementation from interface. And one way to sort of separate something interface from an implementation is to write a data structure for the interface and then provide an implementation in terms of an interpreter. And you can have different interpreters that provide different implementations of those features. So the idea is to make a data type for a monadic domain-specific language and then write interpreters over that data type. And so this is not the free monad quite yet, but it leads the way there. So if we were to do a really, really simple monad, that's just the reader monad. So the idea is that you have a reader monad and it's just able to read a value of type env. So reader is often explained in terms of an environment. And so a monadic or a computation that is able to read the environment and provides a result of type A, we could define it as this. And the idea is, well, it has one operation, the get operation or the read operation. And the problem is, of course, you want to sort of communicate. Well, if you have a get operation, you need to not just say, well, I'm getting a value out of the environment. You also need to say what is to be done with the result of that get. And the trick that is used there is you provide a continuation. So get takes as its argument a function that goes from the environment to the next, to the continuation, to the what's a different word that is not quite continuation, to how the program goes on after that, right? So you get a value. Well, you provide the value by passing it to that function, and then the program explains what it wants to do with that value in terms of another program. And when you have this, of course, and if you look at this, well, you can see that this program, this data type cannot stand on its, well, in Haskell, it could stand on its own, but this program is never done, right? So it would be nice if we could sort of break the infinite recursion here and just say, well, this program is done. We just provide another case in the data type, and we provide the final result, which has type A. Okay, that's an idea. Okay, is this reasonably clear how that works? And then I can go and say, well, I can say I can like have like a lowercase get operation, which is just reader env by saying get is the same thing as get of, well, let me program it out, then you can see it by, so what it does is it gets the value, it gets the environment, calls it environment, and then returns that final value. And we can just eta reduce that and write this here, right? That's the same thing. And so, but that leaves the question how we can compose several of these things. And well, we compose them just by using monadic syntax. And how can we do this? Well, we can provide a monad instance. See, now that I've written that in my notes, there's a version I don't really want to use. Let's see if we can do that together. So we want a monad instance. What is the problem? Okay. So it, what? I'm sorry, I can't really justify the fact that Haskell changed to require, I was born, or I was socialized into Haskell at a time when applicative and functor weren't prerequisites for monad yet. So I'm just going to generate instances for them. They're not really needed for what we're doing here. And the idea is, okay, so we can provide a monad instance for this by saying, return is done. And then we can say, well, if we have a, if we have here the bind operator, right? And the bind operator needs to pattern match on, either this, right? So, here's, I'm just going to call this next, right? So if the program is done, and well, if there's one program that's done and some program comes after that, we just call next on the result, right? And the other thing is that if we have a get operation that has a continuation, and that is next, and then comes next, we kind of, we can compose these two things. So, well, the idea is, well, if the, if we slap something onto the back of a program that starts with get, the resulting program is still going to start with get. Again, we need to provide a continuation. And well, we have that environment. What can we do with that environment? We can just call cond on that environment, right? And then can call next on that, I think. No. What is the problem? Occurs check. I'm sorry. Of course, we can't use function composition. Instead, we should be able to do this. Okay. And so you can see kind of how that pushes the bind operator inwards in the monad instance. Okay. And now, you can do that a couple times. and you realize that you're always following the same pattern, right? So you're always defining data types which have a done constructor, and you're always defining your operations, where you provide a continuation as the attribute of the appropriate constructor, right? And so you find yourself doing the same thing over and over and over and over again. And so you could reasonably ask, well, can I abstract over this pattern? So if you imagine, so can I abstract over the readerness, right, of this particular monad, and just sort of extract the monadic essence, right, over reader-specific aspects of reader, right, and extract something like the monadic essence of this, right? And so the idea is that you do a data type that works well. Cat's out of the bag. This is something called the free monad, and so the idea is that later we will do something like this. We will define. So the idea is we will define a type. I'm going to call it reader. Reader this. Reader prime, and the idea is I'm going to call this, and of course we don't want to define done, since that's part of every data type that we use in this construction. So we just want to define the get case, and we want to abstract over everything that is not specific to this operation. And so we still need a function that takes the environment, right, as an argument. And then you can see here in the data type here, there is a recursion here, right? So this is exactly the data type that we're defining. And of course, we don't know yet the data type that this is going to be embedded into. So we're going to have to parameterize over that. And I'm just going to call that not. Okay, so the idea is this is the reader specific part. And then we want to define the rest of that data types. And so F is going to be, F will be reader prime of env, for example, right? When we define the concrete reader monad. And here is the regular A return type of the monad. So I'm not going to call that done, but I'll call it pure, which you will usually find the relevant publication. So pure is same as done, right? And then the other thing is a concrete operation in the monad. So kind of by definition, that's got to be the impure part. And the impure part is going to be, well, so we kind of need to get we need to get the reader specific part in here, right? And so we need to say F. Remember, F is the reader prime thing here. And the reader prime needs exactly the data type that we're defining, right? So here, now you need to apply your abstraction facilities in your brain. So, and so this part here, so the, this part here, that's in reader prime. And now we need to tie the not, and the not is exactly free of F of A. Does that make sense? Okay. And so now then we can, well, I'm just going to go back and define this, call this reader one, since we don't really want that one. The one that we really want is we want to then define reader of env of A is the same thing as free of reader prime of env of A. Okay, and not data, but just a type alias. Does that make sense to everybody? Okay, you're going to ask, well, what does that have to do with my applied problem? But we'll see, right? So the well, actually, we can see that now. So now we have really a data type, that is one effect, right? We have this data type that describes exactly one effect that we want. It doesn't describe the structure of the monad. It doesn't, it has very little sort of boilerplate extraneous stuff. This really is just one effect, right? Data type for one effect. right? And remember, the problem was that we wanted to define a monad that has more than one effect, right? And so, so one way we could do that, I could just say a bunch of effects that is like, it is get something something. I could define a big data type that has all the operations that I want. It has put, it has whatever, printf, whatnot, and so on, right? But of course, this again, defines a big monad, if you will. It would be great if we could combine these data types after the fact. So in one module, we'll define the reader data, the data type for the reader effect. In another module, we define the data type for the writer effect, for the state effect, for whatever effects we want. And if we only had a facility that would allow us to combine these after the fact, so to sort of put several data types into one data type. And that's a long-standing modularity problem in Haskell, and fortunately, Wouter Swirstra solved that problem a number of years ago with a very nice paper called After the Fact Data Types a la carte. So that's not the main subject today, but there's a way to do that with the help of type classes, is to sort of make automatic to have some types after the fact, and then have automatic injections and projections from that data type. So now we've kind of split the problem in two problems, into two subproblems, and one of them is, well, we've defined the sort of monadic essence here, and we'll just see in a moment how that works. And we split the monadic essence from the actual effect, and we can use data type a la carte to combine several effects into one. So there's sort of a paradigm shift where, with monad transformers is always you build up, you sort of, compose your monad out of several monad, transformers. And you sort of remove the transformers as you actually provide implementations. And the new idea is one big monad, well, it's not necessarily big, but we only have one monad, but it's parameterized by the effects, right? Because this, remember, the reader prime data type is one effect, and that's exactly the type parameter here, down here. Okay, that is that type parameters, right? So F describes the concrete effects available, right? And then, so of course, well, for this to work, you need free of f of a to be a monad. And the great thing is, well, we can try that. We can say, well, instance monad of free of f, where, well, what can we do? Return, that's easy. That's just pure. And in order to implement bind, we're going to have to pattern match. So we have, pure result, and compose it with some next thing. Well, that's again easy. We can do the same thing that we did up here. We just call next on result. And if we have impure of some operation, whatever, right? You have an impure operation, and something comes after that operation, then, well, remember that up here we kind of pushed the bind inside. So that's what we need to do here also. So we need to push the bind inside the impure. And the way that works is, well, how are we going to do this? Well, we need to sort of, we have our operation, right? But unfortunately, sort of operation wraps one more layer of F around our data type, and we need to get our we need to get the next thing that we have somehow inside there. And so when you have an operation, you want to apply it inside a data type. What is that? Have you heard it before? You have a data type of A, and you want to apply a function to that A, you use a functor, right? So the way that turns out to work out this way, that you do this, and it type checks, so it must work. Well, it actually does work. So the only problem is that, what is it complaining about here?
You need to use
Yeah, I need to
redo1.
rename that one. What does it have? What kind of problem does it have? Also, here's another one. Okay, so, and then hopefully it's going to complain to us that, no, applicative, just going to cheat again. So this, by the way, cheat, deriding functor applicative. In your spare time, you can do this, but now it just says, oh, well, your f needs to be a functor, right? And usually the functor is fairly easy to define when you have this, right? So in this case, for reader prime, quite easy to define the functor. And that's a construction that's known as the free monad, okay? And that is, I think, the basis for most. So maybe you have noticed there's now a variety of effects libraries available for Haskell. There's probably, I don't know, 10, 12 different effect libraries on Hackage that you can find. And most of them are based on this idea of a free monad. So unlike the monad transformer, where you build up your monad transformer, is you use the free monad and you use data types a la carte in order to have one monad that has as a type parameter all the some representation of the effects that you use. Okay, that makes sense, right? And so that's sort of the mental shift that you make when you move from MTL and monad transformers to those effect libraries. Okay. I should mention one other thing that, and I mean, you don't really need to fundamentally understand how free monads work, but you will. So this is the free monad. You will sometimes find something called the freer monad. Right? Maybe I should mention that just so you know what it is when you see it. Freer monad, also something that Oleg Kiselyov came up with a couple of years ago. One of the problems here, if you look at this, right? If you look at the bind operation, right? You can see that it kind of moves the bind over the impure, right? And you can see, so as you have a chain of binds, if you can imagine that, if you have a chain of binds successively, if they're sort of parenthesized the wrong way, then the impure needs to be pushed inside more and more. More and more binds need to be pushed inside the impures, and you get quadratic blowups, right? And so this is a problem, a potentially quadratic runtime for bind, right? As all these impures and the corresponding binds need to be swapped, right? And so in response to that, Oleg came up with this idea of a freer monad, and in particular, well, it's mainly from the fact is that this free monad, it's not quite free in the sense that f still needs to be a functor, and the freer monad doesn't even need a functor there, and the essential idea is this. Well, I'm going to call that freer prime. The freer is this idea, and I think that's kind of nice because what you do is, well, you do a GADT where I'm just going to call it f pure freer f of a, and then what you do is you do sort of you kind of do this. You have a bind constructor that really corresponds to the bind thing that you have in the monad. So, and the way that works is you have an f of a, you have a function from a to freer f of b, and then you go from there to freer f of b, right? And hopefully you can see, well, this is essentially bind that you have here, right? And so this really is a free structure in the sense is that it corresponds exactly to the primitive operation that you have in the monad. So if you see freer monads, then you have this, and you can use this, a variation of this uses a functional data structure for several binds in a row, right? And avoiding quadratic blowup, right? So one reasonable effects library is called freer simple, for example, and that's in reference to the freer monad that you have there, even though you don't actually need to know about this when you use it. Any questions so far or remarks? Okay. So, so I then realized, okay, there's a bunch of effects libraries now. I should look at them. And so I looked at a whole bunch of them and tried to sort of rewrite my example using those effects libraries. And I came up with sort of two reasonable libraries in terms of how easy it was to get things in there. And I hope you can sort of see the connection to the free monad stuff that I just showed you. So here is one that's called polysemi that I really like. And hopefully, so I'm not sure that I need to go through all the details here, but you can hopefully see sort of the general approach. And it was really easy for me. So after a couple of minutes of playing around with polysemi, I was already able to translate the example. So remember that we had this model action monad in the original program, and this now turns into a model action effect. And remember that when we have these free monad-based effect libraries, is that we always declare a data type that has all the operations that we need in it. And so in this case, remember there was this v parameter. Well, we know it. There's the result parameter. And then we say, well, we also abstract over the monad that later is going to implement this. So there's a tiny bit of the boilerplate here that you need to have this m parameter. But otherwise, these constructors correspond to the operations that we have on our model, right? So there's the current model state operation, which is a model action of VM, and it returns a return value has type model state v. Modify value takes the name of something in the model state, and it takes a function that modifies the associated value, and it returns a model action that doesn't return anything. And then there's eval condition, where you say, well, once you know the model state, then return a bool, and then I'm just going to return a model action that returns a bool. Okay, so hopefully you can see the correspondence and that we had. And now the thing here is, well, these are all capitalized, right? And they're not directly usable in programs. Instead, you define a corresponding function. So you can see here, there's current model state constructor, and there's a current model state function, modify value constructor, modify value function, and eval condition constructor and eval condition function here. And well, how does this work? Well, polysemi, sem is the polysemi monad. So unlike MTL and the monad libraries that provide many different monads, polysemi only provides one single monad, right? And that's an encoding, a tagless encoding, if you will, of the it's a tagless encoding of the freer monads idea that I showed you. So you have this monad, it's always called sem, and you can see that it has a type parameter here, r, and r is the row of effects. And the row of effects is just a type level list. Okay. So so there's just a type level list that says, oh, this computation has these effects, and another computation is going to have a different list there, and then we'll later see how to combine these things. Okay. So now one of the problems is, of course, that the type level list needs to be manipulated at the type level, and you don't really have all the facilities of your favorite programming language are available there. Instead, you need to, so you don't really talk about the list directly, you talk about it in terms of constraints often. So in this case, it says, well, if your row, if it says, well, if you have a row of effects, that row is going to contain a model action effect, and then I can have the current model state operation. And I just call the built-in polysemi function send to turn the effect object, if you will, that you have here into a monadic action. Okay, and same here, right? You always talk about this this row that you have, and the reason for that is, of course, that later we want to combine different actions that have different effect rows, and so we don't want to exactly pin down these effect rows, oh, it's these two effects, because if you have an effect row that has, these two effects, and you have another one that has a different set of effects, then they don't compose. They need to be equal. And therefore, you always allow, this way, you allow that this row might contain other effects in addition to the model action effect. Okay, and this is, how all sort of, if you look at effect handler papers, also, they always have some variable there that talks about the effects that might also be present, but that we're not concerned with in this particular place in the program. Okay, so this is just boilerplate, and in fact, Polysemi comes with a template Haskell macro that just generates those three definitions, so you can see that they're boilerplate, but at that point, you can already construct monadic programs. So, for example, here's ModelState modify, which just, no, I'm sorry, that's not a monadic, that's a helper function. But you can now write programs based on this. Now, of course, any questions so far? Okay. So now, of course, this just provides the interface, right? It doesn't say how these things are implemented. It just says, well, here's a data object that represents the effect that you want to have, but it doesn't explain how that actually gets evaluated. And for that purpose, you then write an interpreter. And here's an interpreter. It's called model action prime. And look at the type here. And that's also typical for these effect libraries, in that it says, and look here, this prime colon is the type level cons. It says, well, if you have a monadic computation, and its first effect is this one, right? Its first effect is this one. Then I can convert that into a monadic computation that has all the same effects as the original one, but model action gets replaced by the state effect. So that's very typical, is that either you write an interpreter that removes an effect, that would be one way to do it. Another way to do it would be to translate it into another effect, and then preferably into an effect that is in the Polysemi library already, and then just use one of the functions there to actually boil it down. So you can see down this function actually removes the effect. So model action V is present on the left-hand side of the arrow, but it's not present on the right-hand side of the arrow. Okay, and we just use the eval state function that Polysemi comes with in order to go down from here to removing the state thing. So here you can see how that happens. So reinterpret is a function in Polysemi, and you just give it a function that says, oh, current model state is the same thing as state.get. And modify value, name of f, is the same thing as state.modify, and eval condition is the same as this monadic computation that extracts the model state and returns the result of applying the condition to the model state. So I thought that was pretty straightforward. I really like it. You can see that I'm partial to it. But again, the question is, even if it's kind of pleasant here, is it actually going to allow me later to compose my program, not just define the individual building blocks? So I had to make pleasantly few changes. So there's a random effect. I think that comes in a Polysemi related package. And now you can see here, remember before, monadic version, for example, transition, it was transition V monad, right? It was parameterized over the monad that it runs in. And now it is parameterized over the effects that are available to it. And so that's why there's an R parameter here, not the monad parameter that was there. But other than that, I just replaced all the monads by R. Very nice, that works out. And then kind of everything that I did was expressed in this way, right? So you always say, well, there's, you always express computations as in some, in the Polysemi monad with some row of effects. And then you just say, well, in order for this thing to work, I need this effect available to me, right? So this is what happens here. So for example, so these all need access to model actions, and the same thing is of course true for events, where we just embed the model action effect as a constraint for the various other things that happen here, right? But notice, I mean, that's kind of, I didn't mention it explicitly, but the real problem that made the MTL version fail is really that we had in that we were embedding effects in objects that were again part of other effects, right? And so that's what happens here, and that makes the types kind of go into a funny knot there. So everything here is unchanged from the original program. We could nicely say then here, again, simulation state, remember that it's parameterized over this R, which is the effects that sort of happen at the event level. And then, well, here it gets a little bit more complicated. Maybe I need to distribute that over several lines. So I wanted a composite effect that explains, well, we now have two rows of effects, right? One row of effects that works at the at sort of the local level, at the original, at the level of the model, and that this is so RM is effects at the level of the model, and RM is effects at the level of the simulation, right? Two different rows of effects. And what this says is, well, model action needs to be part of RM. That's what that member constraint says. And the actual simulation just gets generated by adding state, a state effect of the simulation state to that, right? And here's the part where I had to fiddle a little bit in order to construct it. So I couldn't directly express this. I had to put an equality constraint in there, but it didn't take me too much time. Overall, I found it much more pleasant experience than with the monad transformers. Okay, so far? Okay, so again, I haven't looked at the Slack for a while. Okay, free beer, left adjoint, very good. Okay, so now, and things kind of work out from there. Now there's only one thing that where you need to pay a little bit of attention is here's generate events, right? And generate events is at the level of simulation state effect. But the problem is that you call this delay effect, which is sort of at a lower level. So if you leave this out, it says, oh, it gets you a type error message, and it says, well, there's an infinite type in that I expected, an effect at the level of the simulation, but I got an effect at the level of the model, right? And so that's these don't match. And but what you can fortunately do then in polysemi is you can just call this raise function, which just adds one. You can see that it adds one effect to the row, right? And it automatically figures out which one that should be in order to make things match. So that's something that you need to pay attention to even here. And if you remember the monad transformer version, that had a lift here. So you still need to sort of mediate between incompatible rows and explain how to translate an effect, how to translate the effects in one row to the effects in another row. But other than that, it really goes through smoothly. Here's another raise, for example, but it does tell you when you should do it. And then in the end, you just again write and you write an interpreter as a composition of the interpreters of the individual events, and things work out fine. Notice that here again, as it was with sort of the MTL version, we now explain here exactly what the effects are, right? So it doesn't say members of something in that row, member of something in that row. It exactly says, oh, these have to be in that order for things to work. And then the type system will make things fit. So I think this way of writing programs and composing programs that have effects, that is hopefully going to be the future, and hopefully fulfill some of the promise, I think, that that we gave as a functional programming community in the 90s, but I think we never quite got there, and now we're within striking distance to do that. Okay, questions so far?
Yes, there's one
Yeah.
question on the Slack channel.
Of all the difference. Yeah, good question. Yeah, which one has the best?
Please read it.
Good.
Overview.
Yeah, good. Thank you.
Of all the
So
different
question of all the different
possibilities
possibilities that you have mentioned, what is the more pleasant respecting the error messages that you get when things go wrong? And the answer is also polysemy. So I think by far it's the one that's easiest to use. So which doesn't mean that it always gives really easy to interpret error messages. But for example, if you omit that raise, I think the error message is not great, but it's well, let's see what we get with that one. It's not great, but it's reasonable in that you see that there is a mismatch between two effect rows here, and that you need to in particular that they differ. That they differ. Here's RM, and there's just a state at there's just a state in front here, and that means that you need to call raise. So you figure that out. So I think Sandy McGuire, who designed the polysemy library, spent quite a bit of time to not just to implement custom error messages, and they're usually reasonable. Having said that, though, right? So type inference often breaks down. So you will often have to write explicit type signatures for these things. And of course, that's not quite as easy as having Haskell or GHC infer them for you. But I think it's a nice transition to the other. So that's one realistic library. But it gives a nice transition to the other library that I also found to be quite workable, which is fused effects. And if you look at their mission statement, it says non-goals, good error messages, right? So they aren't as good, and we can maybe figure out. Maybe we can look at that. So we're looking at polysemy, and the other one that I found to be workable is fused effects. So in fused effects, and you can see that, well, the pragmatics are similar in that you define a data type, and the data type has one constructor for each effect that you want to use. The boilerplate is slightly different, so you can see here, but that it also has an M parameter that is the same essentially as it is for polysemy. For some, I don't know, can I leave that out? I can leave it out. Okay, good. But that's essentially the monad, but the example had it, and I just found out that the code I had from a couple months ago didn't work anymore, and the new documentation had this. You can see here that it does not have, when it comes to the boilerplate for defining the function version of this, it's slightly different, but the idea is exactly the same. Well, here you don't talk about effect rows, but sig is again sort of a type level list of effects. And here you say, well, model action needs to be part of that sig, and then, okay, I can define the monad action here. You can see, though, that there's one pragmatic difference in that fused effects doesn't give you that one big monad that is going to do it all. Instead, it will construct the monad for you. And so everything is abstracted over that monad. But the pragmatics are very similar in that, well, even the send function is called the same. However, well, not really. However, you can see here that there's larger differences when it comes to actually defining the semantics of your effects. And the terminology is different. So here is talks about algebra, which is an implementation. So here it explains, well, I can have an algebra that explains a translation from this set of effects to this set of effects. To this, I'm sorry, not this set of for this set of effects with this monad. Okay. And so usually when you have an effect and you describe an implementation of that effect with fused effects, is you explain, you define again a monad transformer, which is something that you don't do in polysemy. So here's a monad transformer, but the monad transformer is mostly boilerplate as well, in that you just say, oh, okay, I'm just going a model action effect, model action monad transformer. We're just going to explain that in terms of the built-in state monad transformer. So, but fortunately, so fused effects is the sort of implementation principles behind it I found to be pretty hard to understand, but you don't need to understand all of it in order to actually work with that library. So in particular, but you see that there's a little bit hiding here in that, well, this algebra type class has a function alg that explains how to implement a certain effect. And so you can see here, for example, there's a context parameter that I think you need to implement higher order effects. So we'll briefly touch that subject later, but for now I'll ignore it. That says, and it says, well, and here you can see that there's here you can kind of see the types a la carte construction in that you always have, because essentially this, this construction here for combining two data types is binary, and the two constructors are called L and R. And so, so you have on the left-hand side, you have this particular effect, and on the right-hand side, you have all other effects. And so you can see here, there's pattern matching on the on our own effects, and it similarly to the way that we did it with polysemi, it explains current model state in terms of state get, modify value in terms of, well, I guess I could have called state modify. I don't know why I didn't do that, but of a combination of state.get and state.put, and eval condition also in terms of state.get. You can see here that you need to make the context happy, because Elch has this type where you need to return a model action state CVM of CTX of A. So you kind of need to functor into the CTX functor. You can see here CTX is a functor. And that's why there's these funny ice cream cones here that inject the values into the CTX monad, but it's all boilerplate. And from here on, essentially, things work just as smoothly as they do with polysemi. You need to, let's look at that type. Again, here's the, similarly to what we did before, here's the monad at the level of the model actions, and here's the monad at the level of the simulation state. And, similarly to polysemi, we need to explain, oh, okay, so at the level of the simulation state, we need to be able to manage the simulation state in a state-like monad, and also it needs to be in the signature, and and here, of course, it's a model action. What you see, though, here is that in fused effects, so this constraint isn't talking about the effects purely in terms of the interface. Here, state C is a concrete monad transformer. It also talks about what happens in terms of the implementation. So those things mix in fused effects, and you have to be aware of that. And it took me a while to understand it. And you can see here it was a failed attempt to do it just in terms of the interface, and that didn't quite work. And that is mainly for reasons of efficiency. So to provide some background, and but again, the actual function implementations worked same as before. Here, oh, by the way, here's something interesting. If we get the simulation state, if we want to get at the simulation state, remember how we talked in terms of the monad transformers before, that it's problematic when you have two different state monad transformers that are wrapped in the same onion, that you need to remember which level you need to lift to. And the same is kind of true with polysemi, in that you need to provide a type. So you can't have two state effects that refer to the same type, right? Because otherwise, then it would not know which one you're referring to. But if they're different types, then it's not a problem. You just need to tell fused effects which one you want, and then it will give it to you, and we'll figure it out. So that works out quite nicely. Coming from polysemi, I wanted kind of this. I wanted to have a function like the raise function that I had, right, which would transform something at the level of the model state or the model action to the level of the simulation state by adding an effect, right? And I was hoping to have a function like that, and it turns out that you can define it just as lift, as the standard lift function from the monad transformers, again talking about the implementation. So where it said, so now we have a raise in exactly the same places as we had with polysemi. But again, you're referring here to the, you're looking sort of at the implementation in terms of monad transformers instead of the interface. So that's essentially what I ended up with, and it turned into and turned into quite a pleasant exercise in both cases, and that I was able to actually get the program to run without too much hassle. So if you want to use, if you're looking for an effects library today, then I think these two are the realistic choices that you have. One is polysemi, one is fused effects, and I think the trade-offs are such that polysemi, I found it to be significantly easier to use. Fused effects is okay to use, and fused effects is slightly faster. So those are the main differences, but both are pretty well fleshed out. They're well documented, and the authors are quite responsive. They've been very kind to me, explaining to me how to do this thing, and get it together. So that was a pleasant experience in both cases. There are some caveats which I'll get to though. Any questions so far? Yeah, is there any possibility to do effects without type level machinery? I suppose there is, right? And I've been thinking about doing that in untyped languages where you also want to also control your effects. But I think here doing the effects, so I'm not sure. So I think there's two. I think there's two levels to this question, maybe. So one of them is, I really want to do effects at the level of the types, right? I want to have the type system inform me what effects are involved in my computation. I mean, I am already in Haskell. The Haskell promises me that my type system is going to document my functions for me. So that's what I want. And of course, in order, some type level machinery is going to be involved in sort of describing my effects. The other question is, I think, is it possible to do effects without type level programming, right? So in both of these cases, effectively what happens is that programs run at the type level that say, oh, here's, you have these 5 effects, you're combining this with this other action that has these 4 effects. How do they combine? And of course, there's a type level computation going on there. And also to sort of project and inject into the right parts of the data types a la carte construction that you have. And I don't think there's any way to do that because, yeah, I don't think there's any way to do that. You have sets of effects and you want to combine them and you want to describe how they combine programmatically. So I wouldn't know any way to do that. And even data types a la carte makes do with pretty modest machinery at the level of type classes, but even there it has overlapping instances and so on. So again, effectively, a program runs at the type level. So I don't think there's any way to do that. Does that answer your question, Jens? Okay, great. So, and you'll find that all of these libraries have some. Unfortunately, all of them have their own. I kind of wish that some of these libraries which sort of split the data types a la carte stuff into a separate library and share that, but they don't. Everyone has their own version of data types a la carte, right? So, so I guess that's sort of the sort of constructive part of what I have to say. I'll mention, I'm sure some of you might have been at MuniHac, where Alexis King gave a great talk on performance, because you can imagine that there are performance implications here, right? When you have any kind of effect, you need to construct an object from that data type, and then you need to run the interpretation over it, right? And that has interpretive overhead necessarily. I think both the fused effects people and polysemi ran. They have benchmarks where the programs are pretty short and where the creation of the effects and their handling is in one module. And so GHC just inlines things to the level where it can deforest the program and remove the intermediate data structure and do fusion effectively. And that's great when that works, but I think, so Alexis, the way I understood it, argued that these optimizations break down when you have larger programs. And of course, we're talking about larger programs when you have reasonably large software architecture. And therefore, the overhead of using this over just using, hard-coded monads is significant. But even there, MTL has, I think she even found MTL to have significant runtime cost. So, and I think Alexis kind of remembered something that I also remembered, or that she helped me remember, was that in the 90s, so one side of it was kind of how to do monads explicitly in the Haskell world. And another one, so there was another school, I guess, to doing monads, which showed that, I mean, one problem is that in Haskell, right, once you move from your pure program to your monadic program, you have to rewrite everything with do syntax, which is another barrier to entry when you're coming from something to Java. And but the scheme community kind of figured out that we have call with current continuation, and from there we can derive other control operators, and these control operators can be used to implement the infrastructure for monads without explicit monadic syntax. So you can just sort of inject your monadic infrastructure into your existing program, which is kind of magic. But you need for this, you need something called delimited continuations. And they kind of connect. They exactly provide this connection between, an effect. Some program describes that it wants to cause an effect, and the actual handling of that effect, right? And maybe another way to think about this is that one effect is that we all know is exceptions, and exceptions have always been split between, we describe what the exception was, and we describe somewhere else how to handle that. And of course, the mechanism that brings these things together, that moves the description of what happened to the handler, is exactly continuations. So that's my naive explanation of what Alexis is right now doing. So she's working on an effects library called F. But the problem is that so I think that is going to be the future, is my personal impression. That because it has significantly better performance than polysemi and fused effects, and it has similar boilerplate to polysemi, so it's quite lightweight. But it requires that GHC provides delimited continuations natively, and so she's proposed a change to GHC to do that, and hopefully that's going to go in there at some point, and then we can all benefit. There also was an ICFP paper a couple of weeks ago by Dan Lyon and a couple of co-authors on how to avoid having to search through through different effect handlers. So maybe backtracking a little bit, what we've seen here in Haskell is always that you provide an implementation of effects in terms of a global function or of an instance of a type class, whereas when you look at programming languages that have been designed with effect handlers from the start, you can handle effects locally. And so this ICFP paper was how to do that also with delimited control, but in the shape of an explicit monad that has delimited control. And so maybe these two things, my hope is that these two things will somehow coalesce at some point and provide something usable. But I think F is realistically is going to be the future. But right now, I think the practical libraries for doing that are polysemi and fused effects. Okay, so that's what I have to say today. Any questions or remarks or discussion? We have quite some time. All right. I hope this is useful for some of you, at least. Okay, and you must be tired after 2 days of Zoom. I know it wears on me when I do that. Okay.
So I'm now going to unmute all of you, or ask you to unmute. You will get a dialogue now. So
yeah, that'd be nice.
When we are unmuted, we can thank Mike for this nice talk.
Oh, thank you. Yeah.
Thank you. Thank you for a nice talk and nice workshop. It was really pleasure to follow along.
Okay, great. Thank you. All right. So I'll check the channel, but if you have any follow-up questions or any comments, also feel free to email me or find me somewhere. Always happy to talk about this. Okay, I think, Tim, then I guess we're done, right?
I guess so.
Okay.
Thank you again.
yeah, thanks everybody. Thanks for the questions, and hopefully see you around. Okay, good. Bye.